Okay, welcome warmly. Today we have a task to calculate involving a planar system with friction. A block of mass m is placed on a rough inclined plane. Calculate up to what angle alpha the block will start to slide. The coefficient of friction is μ. So a simple task, a block on a slope. Theoretically, we should handle it easily, mostly using the knowledge we gained from high school. Let's remind ourselves how it works. First, let's draw our block. Indicate the forces acting on it. And now the crucial information. We know the weight acts vertically downward. This is our weight, let's denote it as G. However, the pressure will always be perpendicular to the surface of contact. So if we have our slope here, we have our angle alpha, but we will need that in a moment. The pressure will act here. And now, is that all? No. We also deal with friction. How do we denote friction? Friction in this case will always act opposite to the direction of movement. If friction didn't act, the block would slide down the inclined plane. So let's denote friction in this way. And now, essentially it doesn't matter which reference frame we assume in this case, but really for inclined planes it's usually more beneficial to use a coordinate system related to the plane. So we draw, let's say this is our x-axis and this is our y-axis. To make it complete, we still need all forces to lie in our coordinate axes, because G clearly does not lie in our coordinate axes. G is at an angle to the xy axis. We need to decompose G into components. We'll draw the components. One direction of action, the other direction of action parallel to the xy axes. So that would be one force. Let's call it Gx, we'll calculate it later. And that would be the second force, let's call it Gy. Of course, we could just as well say that in terms of value, this is Gx. It is exactly the same length. Now we need to mark the angle. And this is something people often have trouble with. Usually they learn it by heart. However, here we will show how to do it correctly. A bit of an intuitive method, but it helps with memorizing. Because formally I could say that by using the similarity of triangles, we see that. However, in a less formal and more intuitive way, I'll show. Let's draw our incline. Look, a part of our incline. And let's mark our force G. Our force G would be located as if here. Because it is vertical. In this case, we don't have to think about it. This vector is transposed. We only care about where angle alpha is located. We know that our directions of action are like this and like that. So in fact, we form such a small triangle, where this is our G, this is our Gx, this is our Gy. And now we actually notice that if the angle alpha is here, we know there's a right angle here. We know there must also be a right angle here. Here are the axes of the Cartesian system. They must be perpendicular here. Let's say there's angle beta here, which we define as 90 minus alpha. How do we know it looks like this? The sum of angles in a triangle is always equal to 180. So we know that 180 equals 90. Equals plus alpha plus beta. So after shortening, it turns out that beta equals 90 minus alpha. Now then, if we have a right angle here, it is also parallel to our x-axis. So in this place, we also have a right angle. That means we have angle alpha here. Well, the matter is very simple at this point. We see that this angle alpha is simply, here is angle alpha. We can already write that Gy equals G cos alpha, which theoretically should be obvious. And not theoretically. We see there is a right angle here. We associate cos alpha with the force or vector next to the angle. So next to the angle we have Gy. Opposite the right angle we have G. And from this it actually turns out that Gy equals G cos alpha. Similarly, Gx equals G sin alpha. From the same notation. So sin alpha equals Gx divided by G. And that's pretty much all the important things. Additionally, we will list the definition of friction. Friction by definition is in times mu. And now let's assume that this system remains in equilibrium. Meaning, if this system remains in equilibrium, we actually need the force to zero out on both axes. So for the x-axis, we can note that the sum of forces equals 0. And the sum of forces is simultaneously Gx. We assume the forces aligned with the angle achievement are positive, and oppositely are negative. Gx minus t equals 0. Then we have the sum phi, n minus Gy equals 0. And now we introduce what we calculated. Meaning for Gx we substitute G sin alpha. Substitute t with n mu. Here analogously for Gy substitute G. Substitute y with G cos alpha. And we actually get a system of two equations with unknowns only, but very simple to solve. And now, to solve this using the simplest possible method, we will write these equations here on the side, one under the other. This way, G sin alpha equals n mu, And in turn, G cos alpha equals n. The transition here is very simple because it's just a shift to the other side. In fact, it's the same n equals G cos alpha, only shifts to the other side. We wrote one under the other. Now we will add these side by side. When we add, we will divide side by side, We will divide these side by side, we get G sin alpha over G cos alpha equals n mu over n. So from here G cancels out, n cancels out. We know that sin alpha over cos alpha is tangent alpha. So tangent alpha equals mu, meaning in the task description, even the mass was unnecessary. One could say in quotes that it was given to mislead, to calculate just the angle for which the system will remain in equilibrium. We do not need to know the mass. It's enough that we know the friction coefficient between the body and the incline. And from this we see that alpha equals the arctangent of mu. Regarding this topic, that's everything. Thanks a lot. Best regards.